Hello class, section 3.2, search with improving and feasible directions. So we had the overarching idea in 3.1 and now we're going to get down to some specifics. So our goal is, given that we have a feasible x0, again, that's can be a problem in and of itself, figuring out that feasible x0, but let's assume we have one. Maybe the feasible region is sort of easier in the D club where it's pretty much any x1, x2 would have done, except a few regions. So we've got one of those. How are we going to get a feasible improving x1? Well, here's the rule we're going to use over and over in this class. X t plus 1, your solution, feasible solution vector at time t plus 1 depends on the previous iterate. And then you're going to update it this way. You're going to point in a different direction, delta x, that's our direction vector. And we're going to go some distance in that vector, lambda. Lambda is going to be a positive value. And so visually what we're thinking about is we have some point xt in whatever dimensional space, but let's stick with 3D, that's where we live in. So we have some point here. And then delta x is going to be a direction from that point. So maybe it is this one right here. And then we're going to go some distance along that, some lambda positive this way, lambda negative would be that way, but we're going to go from our point xt right here, some distance, maybe out to here, and that is your t plus 1. We're going to follow that rule over and over, and that works in n-dimensional space. So I want to start off with an example. This is number 2b. So at the end of chapter 3, open your books, pause the video, get your book out, and let's take a look at this problem. It has several sections. Okay, so he says, assume you're given a initial feasible solution, y0. So just making sure we can change notation easily. And you can write this as a row or column vector. I kind of like to write mine as columns, but so that can be thought of as a vector or a point, and we're going to think of it right now as a point. So we have some point in 3-dimensional space. He says, compute the sequence of points visited if you have these facts. So you're given that the change direction in the next iterate is this one, 1, 3, minus 2, and the lambda is given at 2. Again, we're going to figure out how to get those. For now, we're just making sure we can do the linear algebra, or you might have learned this in Calc 3 as well. So we're going to use the new update rule. Y1 is y0, which was the 0.205, plus how far do we go in that direction? 2 to the 0.13 minus 2. And just simple scalar multiplication and then addition. So 2 plus 2 is 4, 0 plus 6 is 6, 5 minus 4 is 1. So this is our y1. This is the lambda, the delta y for that. And then he gives you the next set of points. He says, okay, well, you got to y1. Now you have another change vector. So y2, compute the sequence of points that you would follow if you were given. Take your y1, 4, 6, 1. And this time you're given the lambda 2 is 1/2. And the change vector is 1, 0, 2. Okay, so we'll get 4 plus 1/2 is 4.5, 5, 6 plus 0, 1 plus 1 is 2. Okay, so this is your next value. So we've moved through at this point 3 points, y0, y1, and y2. And he asks you to do the same thing for y3, and you can just check. Would be a good idea to pause the video, use those values, and you should get y3 is 52.5, 39, and 26. So just want to make sure we can visualize that, those points in space. And maybe we'll just take a few of these and show you in the tool, Calcplot 3D. So you can, let's get rid of some of these. You can enter a point, select point to add. And the point that they started us with, y0 was 205, so I'm gonna enter that. And it'll plot it in 3-dimensional space, or you can plot it in your room in the desktop coordinate system. So there's our point up there. And then we want to get to the next point, y1, we said was 461, so let's add another point. 4, 6, 1. And you got to turn them both on. Put that little, okay, so there we are. We have both of them now. Maybe let's change the color so we can see them a little better, make them a little bigger. Let's just go 8. And let's make this guy. Okay, so there's our, whoops, that wasn't the right point. The red one should be 205. All right, better. Okay, so we have gone from this point to this point following this improving search algorithm. They again told us that this was an improving direction. This is the direction of bettering your objective function value. Finding those delta y's and the lambdas, that's the next part. I just also want to show you that if, let me go write it over here. That if you had to do this as a space curve, 205 plus t times this direction, 1 through 2, which is 2 plus t, 3t, 5 plus 2t. Now, what does that space curve represent? That starts at the point 205, goes in the direction 132, but it does it for any values of t, and it actually creates the full line. So you can plot that as a space curve. So let's just visualize that and we get to review some calculus. The third component was 5 plus 2t. So parameterizing with t this time, so 3t for the second component, and the first component was 2 plus t. And let's see, make sure to change these values. Second. Okay, so here's our space curve, but I've got a typo here. This should be a -2, right? So this was this y0, the first direction vector at the point 205, y0 in the direction delta y1, 1, 3 minus 2. So this should be 5 minus t. So when I put that in, okay, now we see that we have, as long as t is positive, we're shooting out an array. And if I add some negative values over here, let's say, then it extends and makes the line. So, right, so we go from 0 to the next point through there. And if we actually stop this at, if t is 2, if we trace it, whoops, it stops right at that point, right? So the trace is starting at the red point, and then it's moving you along that space curve along the black dot until you get to t equals 2, stops you right there at the blue. So that's how we get to our y0 in red, y1 in blue. Okay, so in our improving search algorithm, if we have an xt that is feasible, we need to figure out with our update rule, what is the lambda and what is the delta x, our direction vector, that is going to be so that xt plus 1 is improving and feasible. So remember, feasibility always has to do with constraints. So we need xt plus 1 to satisfy the constraints. And then improvement, xt plus 1 will be an improving solution if that always relates to the objective function. So if it's a maximization problem, we go from xt has some objective function value, and then at xt plus 1, we're better than that. Okay, so keep those two things in mind. For to be a feasible direction and a feasible step size, it has to be related to the constraints. To be improving, that's related to the objective. Okay, and then we're going to have a couple definitions. The first one, an improving direction. So delta x is our direction vector. That is, if you're at a point xt, you are improving if your objective function value at the next iterate, according to our update rule, is better. For all lambda that are sufficiently small, so they're positive, here's a direction, and I can go just a little distance, and I don't have to go really big, just some small amount, and that'll be an improving direction. Okay, and then we are a feasible direction at some iterate xt if the next one, xt plus 1, written in its update rule form, violates none of your constraints. So it exists some step size that I won't leave the feasible region. So I'm at some point pointing in a direction. As long as there's some lambda that I don't leave the feasible, I can make some little bit of movement. I'm fine if it's a little bit. Maybe this is too far and I'm outside the feasible region, but this was okay. So then I found a lambda that does that. We will quantify sufficiently small when we do other, particularly for the simplex algorithm in chapter 5. Okay, so let's talk about those two ideas with some figures. So let's go to your books. I'm going to share the screen, pause the video, grab your textbooks. And okay, let's look at figure, this is page 100 and 101. Yeah, figure 3.6. Okay, so what he's showing here is if you were at the solution x3, which is at the point 2, 0, 2 along the x1, 0 along the x2, so here's that point. And here's a direction vector. Delta x is -3 in the x1, so 1, 2, 3. Positive 1 in the y2 gets you right there to that next point. That is an improving direction vector. How do you know it's improving? This is from our D club example. So think about the surface that was over top of that with these peaks, peak here and a peak over here. This is showing the contour map. They don't have the labels on the contour map, the z equal k values, but we remember the picture from earlier. Where was that one? Almost this guy, right? So that's the peak, and then there's this other local peak. Okay, back to page 101. Okay, so how do we know that this is an improving direction? Because if these level curves were labeled, they would be increasing, and because this was a maximization problem. Okay, on the other hand, here's a non-improving direction. Suppose you had started at x1 and went towards x2. x1 is the point 0, -4. x2 is the point -1, 3. To move in this direction, which is given by the direction vector -1, 7, I go from the point 0, -4, -1 in the x, +7 in the x2, and I get up to the new point. That is a non-improving point, even though ultimately when I get to x2, that's better. That was a higher peak. What makes it non-improving? Is it that I, at some point, am not in the feasible region, like when I ultimately get there? No, because again, improvement has to do with the objective function. And at first, when I start going in that direction, somewhere along here, I'm actually going down that lower peak, that's local extrema peak. And the definition says, yeah, for sufficiently small lambda, you have to be able to be improving objective function value. So there's a lambda, a big lambda for which it works, but it has to be improving right from the start. Okay, let's look at one more example here. Oh yeah, page. Okay, example 3.5 at the bottom of page 101. How do you find these improving directions graphically? Well, you use the level curves, and here's a nice contour map because it does have the level curves labeled. And so you can move in various directions. You okay, Cheech? My dog's having a little coughing fit. Okay. All right. So you can look at this if you're at Y2, which directions are improving and which ones are not. So is this one a max or minimize? So we want to minimize in this problem. So if I move in this direction north, I'm not minimizing. That's not improving, right? Because I'm going from an objective function value of 30 to 60. I'm not improving there. Over here, if I'm at Y1 and I go in this direction, what am I doing? Where are these? 10, 30, 60. Yeah, this would be improving because we're going down into this valley. And this would be non-improving because we're going up. So we're using a graphical approach there. Obviously, that's only works for a certain set of problems. So we'll be able to develop this machinery to work in RN. Okay. Next thing, given that we have figured this out, we have these two adjectives worked out. We have improving feasible delta x. How far should we go in that direction? Well, another way of saying that, you're at some point, you have a direction, how far do you go? That has to do with your lambda right here. In your update rule, it tells you how far to shoot off in that right. Most algorithms are going to do a greedy approach. They're going to take the biggest lambda that still maintains feasibility and improvement, right? So go as far as you can. Back on our polytope, that little bigger polytope that I have, let me get it. Again, we'll eventually be able to define this as a linear feasible region. All sorts of flat objects created this. And I might be at a point here, and maybe my direction vector is along this edge. I'm going to go as far as I possibly can until I'm no longer feasible, if I'm outside the feasible region, so I would stop at this next point. And that's why ultimately in chapter 5, we're going to say that the simplex is an edge traversing algorithm, right? Following this edge to get the next point. Okay, I'm going to erase the board. Okay, I want to look at number 6b at the end of the chapter. So pause the video, pull out your textbook. Let's get to that one. In this problem, they give us a set of constraints. So this is a mathematical program. We know from the constraints, just looking at it, the constraints are linear, but we don't know about the objective function. They didn't give us any information, linear, nonlinear, we don't know. It doesn't matter though, because we're really just going to focus on these constraints to answer this question. So they give us a couple facts. They say, here's the first point you're at. So in part B, they give us an x vector of 8, 5, 3. And then they give you a direction vector. In this case, -2, 1, -1. And the question is, find the step size lambda. In fact, let's make sure you got the wording exactly right. Determine the maximum step size that preserves feasibility in this direction at this point. Okay, so we're not asking about improving in this part. We're just asking about feasibility, which is why they only needed to give us information about the constraint set. So we want to say, what's the biggest lambda that I can go in? Maximum lambda that I can run in this direction from this point. So again, some point in R3, some direction, how far do I go along that and maintain feasibility? Well, think about what that means. Feasibility means you have to satisfy your constraints. So we need the x1 that is built according to our update rule, x0 plus lambda times the direction. So we're gonna use that over and over again. So just using our linear algebra, this becomes 8 minus 2 lambda, 5 plus lambda, 3 minus lambda. So again, this is really just a parameterized space curve, this time parameterized off to lambda. So you could plot it in CalPlot3D, just replace the lambda with a t, and again, you're now moving along that line. Well, it has to satisfy our constraints. Let's start with our simple constraints. Each component of that vector, x1, x2, x3, those are 3 components, has to be greater than or equal to 0. So really, I'm going to get 3 inequalities here. But we also have the main constraint that also has to be satisfied. So we get a 4th inequality. All of these inequalities have to do with lambda. So we're going to have a system of 4 inequalities with 1 unknown lambda that we want to solve for. All right, so let's do a little simplifying. The first one says 8 minus 2 lambda is greater than or equal to 0, moves it up around. 8 is greater than or equal to 2 lambda. 4 is greater than or equal to lambda. So lambda has to be less than or equal to 4. That's what we get out of the first one. The second one says lambda has to be greater than or equal to -5. Really nothing to worry about there because we need lambda to be positive anyway. So don't really have to worry too much on that one. Next one says 3 is greater than or equal to lambda. So lambda is less than or equal to 3. And now we have to do a little algebra on this one. So we have what? Well, I'll just write it all out. 8 minus 2 lambda minus 10 minus 2 lambda plus 9 minus 3 lambda less or equal to 25. Let's see. Minus 2 plus 1 is -1. Minus 4 minus 7 lambda less or equal to 25. So 7 lambdas, I'll bring that over, minus 26. So minus 26 over 7, let's see, so lambda has to be greater than minus 26 over 7. Again, a -1 doesn't really matter. We know that's got to happen. So it's really these two I have to take a look at. We want to choose the biggest step size then, because we need to make a lambda that satisfies all of these constraints. Let me circle the 4 that we're looking at here. This one, this one, this one, and this one. So we need to satisfy all of those circled in green. And we want to take the biggest one. So what's the biggest one that'll do that? You might try 4, but if lambda is equal to 4, that satisfies 4 is bigger than this negative number. 4 is bigger than this negative number. 4 is not less than 3. So that's not going to work. The biggest one that satisfies all of them is we need lambda equal to 3. Does that satisfy all 4 of them? Yes. That's the biggest we can do. We're bigger than this negative, bigger than this negative, less than or equal to 3, yes, and we're less than 4. So this is the maximum step size that we would go. Again, our visualization at a point in a direction, go 3 units along that to the new point. Okay, we're going to close this section by looking at page, what is this? Page 106 in our books. This algorithm in a box, algorithm 3A. We're going to have several algorithms this semester. This is our first algorithm box, the improving search algorithm. So I want you to pause the video and read that. All right, so a few questions. So we have to be given a starting feasible solution. We start at index 0. We're going to move. If no improving direction exists, then you stop. Under mild assumptions, this is a local optimum. So why does it say mild assumptions? I want you to take a look about, think about that, and then you'll read on the next page answers that for you. Okay, but in most cases, this is not, you will have an improving feasible direction to go to. You don't, x0 rarely is the optimal value. You don't get that lucky if you're parachuting in, right? So usually there's a direction that improves and is feasible. So we're going to construct that improving feasible direction. Again, we'll get some information on how to do that in chapter 3. He's assuming use one that I've given you. It'll take us into chapter 5 till we figure out how to actually get that direction vector. For now, we're practicing the algebra constructing these. But we can get a step size, right? We know the step size to get a feasible direction. We look at the constraints and we do like this problem we just solved here, get the maximum step size. And how do you check if that moving in that direction in that lambda is an improving direction? You check your objective function. If from x0 to x1, you're making progress, your objective function has improved. If it's a maximization, it's increased. However, though, what happens in this algorithm if you get to step 3 and lambda could be infinite? There's the biggest step size you can go. There actually is no restriction. Well, there was no 3 or 4, right? It was only lambda had to be greater than this or greater than that, greater than this, greater than that, it's maybe 4 or 5 different things that it's greater than, well, there's nothing restricting it. And so in that case, if lambda is ever returned, that it is infinite, lambda is infinity, then the model is said to be unbounded. And what it would look like, you might have a feasible region in R2, x1, x2. You could have an infinite feasible region. Maybe it's all this here. And you want to maximize maybe in that direction. So it just keeps on going. What's another example of an unbounded model? Maybe something like this. Just to think geometrically, again, back to our Cal 3, maybe we wanted to maximize x1 squared plus x2 squared subject to x1 greater than or equal 0, x2 greater than or equal 0. So now we are in the non-negative octant in 3-dimensional space. So what does that surface look like? Maybe you recognize that is a circular paraboloid, one of those bowls, right? A upward facing circular paraboloid. And if you're maximizing and you're just taking the quarter of that paraboloid that lives in the non-negative octant and you're maximizing, you just keep on going to infinity. There is no max. On the other hand, if you're minimizing, there is a min. So the problem can be unbounded in one direction, but you have an optimal solution in the other direction. Okay, so problems from sections 3.1 and 3.2, your suggested homework is numbers 1A, 3A, 4A and B, 5C and D, 6C. Oh, I'm gonna stop the share so you can see that a little better. Suggested homework for 3.1 and 3.2, just doing sections of those problems, don't do the whole ones.